Welcome to Gradient Canvas. Today we're going to learn about byte-pair encoding, the surprisingly simple algorithm that learns a language model's entire vocabulary by doing one thing over and over, gluing together the most common pair. Last time we saw that a language model never reads your words, it reads tokens. The word strawberry becomes star, aw, berry. A giant word shatters into familiar chunks. But that raises a question we quietly skipped. A tokenizer has a fixed list of tokens, around 100,000 of them, and ization, berry are all just sitting in that list. So who wrote it? Did an engineer sit down and type out 100,000 word pieces by hand? Of course not. That vocabulary is learned, grown automatically from raw text by an algorithm so simple you could run it on paper. Today we run it live. Here's the twist. This algorithm wasn't invented for AI at all. Back in 1994, Philip Gage described byte-pair encoding as a way to compress data, make a file smaller. The idea is almost silly. Look at your data, find the pair of symbols that occurs most often, and replace every copy of that pair with a single brand new symbol. Then write down what the new symbol stands for. The data just got shorter, and you repeat. That's the whole trick. And 30 years later, it's how essentially every large language model builds its vocabulary. Now point that exact trick at language. We start at the finest possible level. Every word is just a sequence of individual characters. Nothing is glued together yet. This is the most broken up, most expensive way to tokenize. Here's our training text. 5 little words with how often each one shows up. The 15 times, then 7, there 5, they twice, that 3 times. Our starting vocabulary is simply the distinct characters that appear AEHNRTY, 7 tokens. Watch what BPE does to them. One pass of the algorithm. Look at every adjacent pair of tiles across the whole text and count how often each pair appears, weighted by how common each word is. The pair T followed by H shows up at the start of every single word, 32 times in total. That's the most frequent pair in the entire corpus. So we merge it. Every TH everywhere at once fuses into a single new token, H. We add one rule to our merge list, TH arrow theeth, and our vocabulary grows from 7 tokens to 8. That's it. That's one step. Now we just do it again. Round 2, now the most frequent pair is our new TH token followed by E 29 times. So then E fuse into the. And if that sounds familiar, it should. That's exactly the teaser from the tokenization video. TH becomes the E becomes the. Except now you can see it isn't a hand wave. It won on the counts. And notice this merge glued a letter onto a token we built in the previous round. Merges compound. Now look at that, the token. It isn't trapped in one word, it's shared. The exact same the piece sits inside the then, there, and they. 4 words, 1 reusable building block. That sharing is the entire reason this works. Round 3. The most frequent pair now is the followed by N 7 times, so it fuses into the whole word then. Watch one of those shared pieces get swallowed into a bigger token. 3 merges in, and our field of single characters has collapsed into a handful of fat, reusable tokens. So what did training actually produce? Not a neural network, not magic. Just this, an ordered list of merge rules sitting on top of the starting characters. That list, applied in this exact order, is the entire tokenizer. And here's the knob that controls everything. The size of the vocabulary is simply how many merges you choose to run. We stopped after 3, so we have 10 tokens. Run 50,000 merges instead, and you get GPT-2's vocabulary. Same algorithm, same loop. You just don't stop as early. Training's done. Now let's actually use it. Take a word the tokenizer never saw in training, these. First break it into characters, THESE. Then walk down the merge list in order and apply every rule that fits. Rule 1, TH fires. Rule 2, the E fires. Rule 3 needs the N. There's no N, so it's skipped. Done. These is 3 tokens, the SE. We just tokenized a brand new word using a piece we learned from completely different words, and it shows up in surprising places. The word other tokenizes as O, the R, with R the sitting right in the middle of it. Fixed vocabulary, unlimited text, the promise from last time, now delivered by the algorithm. One loose end. I said we start from characters. But watch what happens with a word like this. It has letters our tiny vocabulary never saw, so there's simply no token for them. Zoom out to the real world. There are over 100,000 Unicode characters, plus every emoji, and a brand new one could always show up. So modern tokenizers, starting with GPT-2, pull a beautiful move. Don't start from characters, start from bytes. Every piece of text on Earth, any language, any emoji, is stored as a sequence of bytes, and there are only 256 possible byte values. Now, nothing is ever out of vocabulary, ever. A strawberry emoji is 4 bytes, the word cafe is 5. BPE then merges frequent byte pairs exactly like before. That byte in Byte-Pair Encoding, that's where it lives. Let's put real numbers on it. GPT-2's vocabulary is 50,257 tokens, that's 256 bytes, plus 50,000 merges, plus one special end-of-text token. GPT-4 roughly doubled it to 100,000, GPT-4o doubled again to 200,000. Bigger vocabulary means each token swallows more text, so a sentence becomes fewer tokens, cheaper and more fits in the context window, but the model's output layer gets wider. And to prove this isn't a toy, ask GPT-4's real tokenizer to split the word newer. It gives you new, then the exact frequent pair merges we just built by hand. The algorithm you watched on 5 Little Words is the one that ran on the entire internet. So, Byte-Pair Encoding in one breath. Start from bytes, find the most frequent adjacent pair, glue it into a new token, and write down the rule. Repeat a few thousand times. That ordered list of merges is the whole tokenizer, and its length is your vocabulary size. Every token you've ever seen a model use, the ization, a leading space transformer, earned its spot by being frequent enough to merge. But a token is still just an ID, a number in a list. The real question is how a number comes to mean something. That's the next step. Each token ID becomes a vector, and meaning turns into geometry. That's embeddings, and it's where we go next. Thanks for watching. This is Gradient Canvas, where we make AI beautiful and understandable. If you enjoyed this and want to understand AI concepts, please like, subscribe, and share it with others. Join us to explore more AI concepts from neural networks to transformers. See you in the next video.